Now that we have learned the appropriate way to draw force diagrams, we're going to learn how to do some very simple calculations. The first thing we need to talk about is a concept called the net force. The arrows in our previous force diagrams are individual forces, but the behavior of the object depends on what happens when we put all of them together. This is called the net force. So what you need to write in your notes is that the net force equals all of the forces combined. We use a special symbol for the net force. The strange letter in the front is the Greek letter sigma. In math, this symbol means to add them all together. So this really just is the sum of the forces, or adding up the forces. Why do we do this? Why do we care about the net force? It's because it tells us something important. The object will accelerate in the direction of the net force. So if we put all those arrows together, we can figure out which way the object is going to accelerate, and that allows us to make very accurate predictions of where the object will be in the future. A few days ago, we talked about the independence principle, and we learned that the x and y dimensions are independent of each other. What that means today is that when we add the forces together, we deal with the horizontal and vertical forces separately. That means that we're going to have to do two calculations. The net horizontal force is sigma F with an X, and the net vertical force, which is sigma F with a Y. Remember that the letter X is associated with horizontal motion, and the letter Y is associated with vertical motion. Before we do any math, we need to establish our positive and negative directions. We use the same system that your math teachers use. So, in the x dimension, any arrow that points to the right is a positive force, and the left is a negative force. In the y dimension, any arrow that points up is a positive force, and down is a negative force. Again, this should feel natural because it's the same system that your math teachers use. So let's start doing some calculations together. If you flip your note page, you'll come to some example problems. And the first problem looks like this. Notice, whatever this object is, it's experiencing a weight of 75 and a tension of 100. The capital N is the unit for force, which is called the Newton. We're going to learn a lot more about what a Newton is in your next lesson. So for today, you just need to know that the letter N is the unit that comes with forces. The first thing we're going to do is take the answer box, which is below the diagram, and split it in half. On one side, we're going to look at the x dimension, or the horizontal forces. And on the other side, we're going to look at the y dimension, or vertical forces. So the first thing we do is we ask ourselves, were there any forces pointing to the right? And in this picture, there were none. Were there any forces pointing to the left? In this picture, there were none. That makes the x dimension really easy to deal with. The sum of the forces in the x dimension equals 0 newtons. Nothing is happening horizontally. In the vertical dimension, we ask ourselves if any forces are pointing up. Yes, there's 100 newtons in the upward direction. Are any forces pointing down? Remember that down is negative, so instead of writing 75, I write negative 75. Now I'm going to put these forces together. The net force in the y dimension equals 25. That's because 100 minus 75 equals 25. Because we got a positive answer in the y dimension, that means that our net force is pointing in the upward direction. The reason this matters is because it tells us what direction we will accelerate. Back on the original diagram, I want you to write the letter A for acceleration and then draw an upward arrow. This is how we tell people that this system, when all of the forces are put together, will accelerate in the upward direction. If you look at the rest of this row, you will see that there are 3 more examples. Please pause the video now and give the students a few minutes to work through these examples. Make sure that they're on task, and when it looks like they're ready for the answers, you can continue the video. Here are the answers to those 3 problems. Please check your work, and if you made any mistakes, fix it. In the first diagram, the net force in the x dimension was 0, and the net force in the y dimension was negative 10. This means that the object is going to accelerate in the downward direction. So in our diagram, we draw a letter A with a downward arrow. In the next example, the x dimension is 0. The y dimension is also 0, which means the acceleration will be none. This object won't accelerate because the net force is 0. The last example, the x dimension is negative 100. The y dimension is 0. This means that the net force is to the left. So in our diagram, we write A for acceleration with a leftward arrow. These examples are pretty simple, so we're going to make things a little more complicated. On the next row, you have some examples that have a lot more arrows. We follow the same process. So, in the x dimension, we ask ourselves, are there any forces pointing to the right? Yes, there was friction of 12. Are there any forces to the left? Yes, there was tension of 20. Remember that left is negative. If I put this together, I get a net force of negative 8 newtons. Because it's negative in the x dimension, this means the net force is pointing to the left. In the y dimension, are there any upward forces? Yes, there's a general force of 15. Are there any downward forces? Yes, there's a weight force of 25. Because it's in the downward direction, I record it as a negative 25. If I put these together, the net force in the y dimension is negative 10. Because I have a negative force in the y dimension, That means that the net force is downward. When I draw my final answer in my picture, I need to include both left and down in my arrow. And the way that I do that is by drawing the arrow at an angle. So my acceleration vector is going to point down to the left at an angle. This is the direction the object will accelerate. There are 3 more examples on this row. Please pause the video so that the students can try to work through these examples on their own, and then when they're ready, you can continue the video. Here are the answers. Please take a moment to check your work and correct any mistakes that you made. In the first example, the x dimension is 0 and the y dimension is 50, which means our acceleration vector points in the upward direction. In the next example, the x dimension is 50 and the y dimension is negative 55. This means the object will accelerate at an angle that points down to the right. In the last example, the x dimension is 40, the y dimension is 30. If we put these together, we see that the acceleration of the object will angle up to the right. We're going to finish today by talking about something called balanced forces. If the net force of a system is 0 in both directions, then we say the system is balanced. It doesn't mean there are no forces, just that when you add them all together, you get 0. It is important that both the horizontal and the vertical analysis gives us a 0. If a system is truly balanced, then we use the word equilibrium. Equilibrium just means that the forces are equal, and so the system won't change. There are 2 kinds of equilibrium. The first is called static equilibrium. It means the forces are balanced and the object is not moving. The word static means to stay the same. And so in this case, the object's position is staying the same. Static equilibrium is related to Newton's first law because we know that an object at rest stays at rest unless it is forced to move. Well, if the net force is 0, that means that it has not been forced to move, there will not be acceleration, and the object will continue to do what it was already doing, which in this case was nothing. The second type of equilibrium is called dynamic equilibrium. In this one, the forces are balanced and the object is moving at a constant speed. Remember that inertia will keep the object going even though the net force is 0. This is hard for some students to believe, but it does make sense if we think about Newton's first law. We know that an object in motion stays in motion unless it is forced to stop. And in this case, the net force is 0, which means it was not forced to stop. The object will not accelerate. It will continue to do whatever it was already doing, which in this case was moving forward at a constant speed. So, dynamic equilibrium is strange, that you can have a balanced system and the object can be moving. The important thing is that the object is maintaining a constant speed and direction. In other words, it is not accelerating.